Dedicated chemistry students, today we're going to go over this multiple choice review sheet for the gases and heat test. For problem number 1, it says Tim wants to store 0.122 moles of helium gas at 203 kilopascals and 401 kelvins. Which is the volume of the helium gas needed for storage? So in this case, we are given moles, pressure, and temperature, and we're asked to find volume. So we're going to want to use the formula that involves pressure, volume, moles, and temperature. PV equals nRT. So in PV equals nRT, we're solving for volume. So we'll say that volume equals nRT over P. So our moles is 0.122 moles times R, the gas constant. Now since our pressure is in kilopascals, we'll use the gas constant in kilopascals, 8.314, times our temperature, 401 kelvins, it's already in kelvins, divided by our pressure, 203 kilopascals. So we take our calculator, and we get 2.00 liters, which is C. For 2, 55 milliliter sample of gas was enclosed in a flask at 22 degrees Celsius. It was placed in an ice bath at 0 degrees Celsius while the pressure was held constant, which is the final volume of the gas sample. So here, we're starting at one temperature, we're going to a different temperature and trying to find what the volume is. In this case, we are changing conditions, and if you are changing conditions, you use the combined gas law where you start with one set of pressure, volume, and temperature, and you go to another. So we're going to use that one. So if in this case, our pressures stay the same. So P1 times our volume, 55 milliliters at temperature 1, 22 degrees Celsius, plus 273, we need to convert that to kelvins, 295 kelvins, equals, and we don't know what the second pressure is either, we're trying to find the new volume, and it's at a new temperature of 0 Celsius, which is 273 kelvins. Now, if the pressures are the same, we could plug in any number we want for pressure, like 1 and 1 or 3 and 3. But whatever they are, if they're the same, they cancel out on both sides of the equation. So to find V2, we take 55 divided by 295 and multiply it by the 273. And we get 50.9 milliliters, which is C. For number 3, a gas at STP has a volume of 37.8 liters. If the temperature is raised to 22 degrees Celsius and the pressure changed to 50 kilopascals, what's the new volume? So this is, once again, we have a gas at standard temperature, standard pressure has that volume. So this temperature and pressure go with that volume. And then we change conditions. So once again, we're using the combined gas law. So our initial volume is 37.8 liters. We're at standard pressure and standard temperature. Standard temperature, 273 kelvins. Standard pressure, there's a lot of them on here, but we need the pressure that matches the units on the other side, kilopascals. So we're going to use 101.3. Be careful, don't use the gas constant, use standard pressure. So 101.3 kilopascals. And that equals, well, our new temperature is 22 degrees Celsius, which we already found before, is 295 kelvins. 50 kilopascals times V2. So our volume, we're going to cross multiply and solve for V2. is 82.8 liters, which is D. All right. Now, problem number 4 works on a very similar way. It talks about volume and temperature. It doesn't even mention pressure, so just like in number 2, you ignore it. The answer to number 4, by the way, is B. Number 5 says, what is the volume of a 1.6 moles of helium gas if it's kept at 2 atmospheres and 253 kelvins? Here, we're not changing conditions. It just wants to know volume given moles, pressure, and temperature. So this is going to use the ideal gas law, PV equals nRT, or V equals nRT over P. Our moles are 1.6 moles times our gas constant in atmospheres, which is 0.0821, times our temperature in kelvins, which it already is. If you use Celsius on this problem, you'll get it wrong. Divided by our pressure, 2 atmospheres. We multiply all that out, and we're going to get 16.6 liters, which is A. Number 6, negative 13 Celsius, negative 13 plus 273. That's 260 kelvins. That's A. If you forget how to convert Celsius to kelvins, it's on your reference tables right there, page 3. Number 7 works very similar to number 3. Number 8 works very similar to number 5, except we're just solving for moles, because it wants to know how many moles given those. We'll work out. Number 7, by the way, the answer was A. Number 8, we're solving for moles. So N equals PV over RT. Our pressure is 1 atmosphere, 5 liters. Our gas constant in atmospheres is 0.0821. And 25 degrees Celsius is 298 kelvins. So N comes out to be with 0.20 moles. Because if you take 1 times 5 divided by 0.0821 times 298, you get 0.2 moles. Number 9. What quantity of nitrogen has a volume of 11.2 liters at STP? Well, if you have 11.2 liters, and we're trying to find either moles or grams, if we're at STP, you can approach this 2 different ways. You could plug into PV equals nRT and substitute in standard pressure and standard temperature for your pressure and temperature and solve for moles. Or, if you remember right here on the front of your reference tables, there are 22.4 liters in every mole. So we can go directly from liters to moles. 1 mole is 22.4 liters. And this equals 0.5 moles. 0.5 moles is not an option. So it's not A and it's not B. So let's try converting it to grams. Now think about nitrogen. If you remember nitrogen on the periodic table, that's what makes this problem a little bit super tricky. Nitrogen is one of the diatomic elements, the one that comes in pairs. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen. So it's not just N, it's N2. So its molar mass is not 14.01, but twice that, 28.02 grams per mole. So you multiply that out, and it equals 14.0 grams, which is C. This question's a little bit on the trickier side. Number 10. How many grams of ice will melt at 0 degrees Celsius if 275 joules of heat energy is absorbed? Here we're melting. That as you will recall, is a heat of fusion problem. So Q equals M times the heat of fusion constant. Q is our quantity of heat energy in joules, so 275 joules equals a mass we don't know. And then the heat of fusion constant for water is 334 joules per gram. So to solve for M, you take 275 and you divide it by the 334. Your mass equals 0.823 grams, which is A. Number 11. What is the total pressure of a system containing 75 kilopascals of nitrogen, 35 kilopascals of oxygen, 15 kilopascals of carbon dioxide, and 10 kilopascals of argon? So we've got a bunch of different gases with different pressures, and it wants the total pressure. Well, the total pressure equals the pressure of the first gas plus the second gas plus the third gas, and so on. So the total pressure is 75 plus 35 plus 15 plus 10 or 135 kilopascals, or B. Number 12. If you take this piston and you push it down, as you squeeze those gas particles closer together, you're definitely not increasing the volume. But as you squeeze those particles closer together, they're going to end up colliding more often with the walls of their container, causing the pressure to go up. So 12 is D. 13. These two samples of gas, they definitely do not have the same volume. This one has a larger volume than that one. But if you have the same number of molecules squeezed into a smaller space, which it appears that we do, there's going to be a greater pressure in B. So that's going to be our correct answer. (14). This one, we've got a volume and a pressure, and it wants to know the new pressure at the new volume. So we're going to use combined gas law. Our first volume is 0.75 liters at 760 millimeters of mercury. And it wants to know what the new pressure will be at 1.5 liters. Now they don't give us a temperature, so we'll just assume the temperature doesn't change, so temperatures cancel out. So P2 equals 760 times 0.75 divided by 1.5, or 380.
Mr. Gobble, please call Ms. Spagnoli on channel 2. Mr. Gobble, please call Ms. Spagnoli channel 2.
Millimeters of mercury. Number 15. In this problem, we're increasing the temperature of some water and wanting to know how much heat. Well, if we're finding heat and changing temperature, the only formula with heat and changing temperature in it is Q equals mc delta T. So Q equals the mass, 250 grams, times the specific heat. In this case, it is water. And it's going to be liquid water between 22 and 67 degrees Celsius. Because remember, water is liquid between 0 and 100. So our specific heat is 4.18. And our change in temperature, if we go from 22 to 67, our change in temperature is 45 degrees. Do not try and add 273 to this in this problem. So we take 250 times 4.18 times 45. And we get 47,025 joules. So the best answer for that is going to be C. Number 16. Below is a heating curve. Where on this graph